All right, welcome back. Sorry, I've got my, I know you can't see, I've got my coffee in my hand. I'm going to take a quick sip. The video started faster than I thought. Okay, so in the last video, we were talking about essentially just sort of the basics of a t-test, introducing the idea of testing means, inferences for means, rather than for proportions, right? That you'll see that the process is very similar to last week, right? And then we were also talking about this idea of independent pieces of information in a sample. And that's called degrees of freedom, okay? And in this video, let's talk about this idea of a one-sample t-test, right? We're going to test a sample mean of a single group against some known value, right? Against some known mean, kind of a status quo sort of situation, right? So just like in the Z world, where we had a test statistic called Z, we've got the same thing, but it's called T instead. And this will result in a T value. Pretty cool. Pretty cool. So let's kind of dissect this. You know, everything here should be, you know, at least kind of familiar, and it's okay if it's not. Totally fine. But let's take it one thing at a time. So X bar, that's our sample mean. How do you calculate that? Well, great question. It's the sum of all the things we've got from the first thing to the last thing divided by the number of things that we have. The number of things that we have. Something like that, right? Pretty cool, pretty easy, right? That's a little bit intuitive, or should be at this point. Mu sub naught. I'll write it up here. Mu sub naught, or mu naught. This is just our null mean. Kind of rooted in the null hypothesis. And this, thank the Lord, is always given to us, right? It's the status quo. Very similar to what we saw last week with P naught. We just have mu naught, right? Sample mean. Sorry, the null mean of the population, right? Cool. Or the known mean, right? We're testing against it. Okay, we've got S here. S is the sample, you guessed it, standard deviation. And how do you calculate that? Okay, so again, this formula gets like pretty hairy pretty quickly. So let me actually not draw it like that. There will be, I will show you one example here in a second after this video where, no, not after this video, let me think. No, yeah, after this video, where, you know, it'll be maybe like a test-like question, maybe it'll be on the test. So it's a good idea to kind of know how to do this. We've seen it before, but it's just gonna be the sum from the first thing to the last thing of the xi's minus the mean squared. Hold on, I'm not done, because this is all divided by n minus 1. Hold on, I'm not done, because this is all underneath the square root sign, right? So you essentially add up. You find this value in here first, square it, and then do it again for the next one, and again, add them all up, divide by n minus 1, take the square root, and you're set, right? Again, gets super hairy, and really is only like fun to do with small samples. When it gets more than like 5 things, it's like super annoying. But regardless, good to know. All right, what else? Oh yeah, and n. Well, n is just sample size, the number of things. And that's it, right? So this is all fairly familiar, right? We saw this with the proportion, that idea of proportions, right? With this test statistic. This is the same idea. We're going to plug this value, whatever it is, into, help me out. There we go. into this thing, okay? However, we notice that this is a little different because we have this new bit of information, V. Well, thankfully, V is just the fancy way of saying degrees of freedom, which is n minus 1, right? Which is very easy to calculate. It's the easiest thing to calculate. So if you have a sample, if you have an n equals 11, right, degrees of freedom equals 10. Now, the thing with this tool is you have to put this in first, and then depending on your purpose or what the question is asking, that's when you put in either here or here, right? So what you put in here is your test statistic t. And then what gets spat out over here is a p-value. Pretty cool, right? In fact, since we're not working with proportions anymore, probably just call this p, right? For p-value. Oops. P-value. Good Lord. All right, cool. And same deal here, right? We have those 4 options for x greater than, less than, 2 times, right? So the two-tailed situation, or kind of the middle bit, right? We still have all of that information, all of those options in there, which is great. Okay, so we can also calculate a 95%, or I guess any percent, any level of confidence interval, right? And you'll see here that the general equation, the kind of nuts and bolts of it, are totally the same, right? It's going to be our statistic plus and minus some critical value, in this case, t, right? Not the t that we found earlier, but we have to go in and find this one. And then the standard error, right? And the standard error and the statistic, pretty easy to find, right? The statistic is mu, right? So whatever you find in the end, whatever your sample mean is, right, you will just kind of put that in place. Standard error is just the sample standard deviation divided by the square root of n. That's easy, right? We already had to do that here anyway. Check it out. It's the denominator, right? It turns out that the denominator of your test statistic is always the standard error. Pretty cool. Now here's the deal though. In the last videos, right, last week, we were working with that idea of a z-distribution, right? Which always has a mean of 0 and always has a standard deviation of 1, right? Okay. Always. So those values I gave you for like a 95%, that critical value was 1.96, right? Well, that's because that stays the same, always, because the z-distribution is never changing. It's fixed at that 0 mean standard deviation of 1, right? But the kind of quirky thing about the t-distribution is that it's based on that idea of degrees of freedom, right? So that means that this critical value here is going to be different every single time, depending on what our sample size is, right? Kind of a pain in the ass, but it is okay. It is okay, because how do you find it? Okay, super easy. We still use that tool, right? So the first thing you do is just find your degrees of freedom. So easy, right? So easy. And then, so n minus 1, right? So if you have 10, a sample size of 10, degrees of freedom is 9. All right, that's the amount of independent information you have. Step 2 is you find your alpha. And by find, I straight up mean read the question. You got to look for it, No calculations there. You do not have to calculate alpha. You just it's given to you, always. It's always given to you or chosen ahead of time. So if it's 0.05, alpha equals 0.05, that's your alpha. And that's it. And then all you have to do is but enter step 1, step 2 into the T tool that I just showed you using that two-tailed option. And then what gets spat out on this blue box over here is that critical value. Okay. Now you can dork around with this in the z-distribution to kind of see, to kind of recreate that 1.96 if you want, right? Or you can just do this every time and just say, F it, whatever. So here's the general idea, right? You put in step 1. So if you have, let's say that n equals 10, well, your degrees of freedom is going to be 9. And if your alpha is 0.05, just plug that in, and then get whatever gets spat out here is then your your critical value, right, for that confidence interval. Okay, so if you follow this roadmap, and also, here it is, 2 tails. You can tell it's 2 tails because of the 2, right? But whenever you do this, it'll spit out your critical value, right? That multiplier for your confidence interval, right? So let's just kind of recap here because I want to make sure we're all on the same page. Let me get rid of this. In this case, when you're trying to find the p-value based on this test statistic, put in your degrees of freedom first, then your test statistic, and then what gets spat out is your p-value. When you're trying to find the confidence interval, you put in your degrees of freedom always first, and then you put in over here your alpha, and then that spits out this value, right? Okay, so no tables there. You have to go find it every time. There are no tables, well, there are some tables that are not as convenient as the one I made you for the last one. So, you can, if you know how to work around those things, it's totally fine. But do this each time and you'll be set. I promise. All right. I'm going to take a quick sip of coffee, read this question before I start reading it. Dang. Okay. I feel so much better. Wonderful. So we have an example. The total individual weights of garbage discarded by 62 college students during finals week has a mean of 35.5 pounds with a sample standard deviation. And this is the sample mean, right? With a sample standard deviation, so that's S, of 15.2, okay? Test the claim that college students throw away more trash than the national average of 30 pounds, okay? All right. And then, if statistically significant, find the 95% confidence interval for the for the population mean, where the population mean is college students' households, right? So this is not for everyone in the nation or everyone everywhere, but just the specific kind of group of people we're talking about. College students. Great. Okay, so what do we need to do first? Why don't we just write out what we have? So we have N, that's 62. We've got the mean, we've got the sample mean, that's 35.5 pounds. We have our sample standard deviation, which is 15.2. That's great. And then the national average, mu naught, given to us, right? Now, this is also given to us, but we could have calculated it that way if we had the data. But that's okay. So then our mu naught is 30 pounds, right? Yes. Okay. And now check this out. So we're not given an alpha, right? But we are given this, 95% confidence. That means that our confidence level is 0.95. That means our alpha is 0.05. How about that, right? Now we have straight up everything we need to find, well, first to find our test statistic, but also to test this whole hypothesis, right? That the national average, do students throw away more than the national average, okay? So we've got this research question. Is the average amount of garbage discarded by college student households greater than the national average? Okay, this is step one, right? Step one. All of the steps are the same, right? From last week, right? So step one is formulate your research question. Step two, I don't know what the heck that's doing there, but this is step two, where we, let me cut this off too. Our statistical hypotheses, our null hypothesis, is that, okay, mu equals 30, right? Mu equals mu naught, right? So our new sort of, we're trying to estimate the whole population, right? And then our one-tailed hypothesis, we have some direction here, right? We have some direction that our sample, when we relate it back to the population, is greater than 30 pounds, right? Greater than mu naught, okay? So that's step two. We already have the degrees of freedom. We did that, right? Did we do that? No, we didn't. But that's okay. So 62, right? That's n minus 1. That's 61. That's the amount of independent information we have. And check this out. Sorry, I just wanted to see ahead there for a second. Here is our test statistic. And let me make this bigger too. I don't know why it's gotten all small all of a sudden. Okay. So T equals our X bar, which is, 35.5. Cool. Minus 60. No. 30. Divided by sample standard deviation is 15.2. Very cool. Let me make sure. Yeah. 15.2 divided by, I'm going to put this in parentheses too, the square root of 62. Okay. So here's the deal. Here's the deal. This is where I get tripped up a lot when I'm doing this. We have our sample size here, where that comes into play only when you're calculating the test statistic. The degrees of freedom come in when we're actually making inference, trying to make that p-value, right? So do I have all of that information? I think I do. Yeah, I think I'm set, right? So we can kind of see where that's going. And if we work out the math, it turns out that this test statistic equals 2.89. Okay, what do we do with that? Well, we just plug it into this. So before we even look, right? We plug it in, right? We have our degrees of freedom here. So n minus 1, which is 62 minus 1, which is 61. We plugged in our test statistic, kept the two-tailed option, and then we got a p-value of 0.00532, right? So what does that tell us? Well, so our two-tailed p-value, if the question was, are college students, is the household of garbage they throw away, right? Are the households different than the known mean, right? Different than the national average, okay? That is not the question. The question is, are they throwing away more than the national average, okay? So what we have to do in that case, we just take our two-tailed p-value, and divide it by 2, right? Divided by 2. So essentially what's happening here, we can kind of see if we zoom way in, right? We have this tail and this tail. So we're looking at the probability that it's either this way or this way. We do not care about one of these directions. We actually really only care about this direction, right? So that means that we only need one of these tails. There are 2 tails, so we'll just divide by 2, and that will spot us that last tail there, right? Cutting that area in half, essentially. Okay, cool. So it turns out that the one-tailed p-value is 0.0026. Is p less than alpha? Let me draw that better. It looks like a C. Is p less than alpha? It sure is, right? In fact, it was less than alpha in both situations, right? So here's the kind of deal too. If you have a two-tailed p-value that is already less than alpha, right? So in this case, 0.05. And here's another thing too. Our alpha is 0.05, right? This here is 0.005, so it's much less, right? So the deal is, like, if your two-tailed p-value is already less than alpha, that means that your one-tailed is also going to be less than alpha, right? Which is great, okay? So the p-value in this case for our specific research question, is it more than the national average? Do we have evidence? We sure do, right? So we move on. So the conclusion here is that we reject our null hypothesis, that our sample, right, equals the known population, right, or the national average in this case. Okay, that's the null hypothesis, but we reject that. We reject that, right? We do not have evidence that they are the same, okay? Or we have evidence against the null. We have evidence against the null in this case, right? So the conclusion in the actual context is there is sufficient evidence to support the claim that the average amount of garbage discarded by college student households, good Lord, is greater. It is greater than the national average of 30 per week, right? 30 pounds per week, okay? So we have evidence that college students are throwing away more than the national average, right? But what is the actual population estimate, right? Because we are only able to say, did we find evidence against? Yes or no. Now we need to figure out the actual population estimate. Now we can't find a specific value, but we can find a range of values where that mean is, okay? So we just make a confidence interval out of that. Easy peasy, right? So we need to find first our degrees of freedom. We've got that, 61, n minus 1. We know our alpha, it's 0.05. Easy peasy, right? Then we just got to plug these two things into our t-distribution tool using that two-tailed option. Always use the two-tailed option when you're making, another thing, even when in this class, and only in this class, when your question, it has that direction, still use the two-tailed option, right? In other classes, you'll learn it slightly differently. In this case, I just want the range, right? I just want the range. Okay, and then whatever is the resulting value is your t-crit, okay? So let's take a look. 61 degrees of freedom, right? And then I plugged in my alpha, right? So this is first, this is second, 0.05. That spits out my test statistic, 1.99962. We will round that up, make that 2, right? We'll make that 2. That's just easy enough, okay? So let me write out what's kind of going on. We found this to be the mean. And what we're going to do here, we're going to plus and minus our t-crit 2 times our standard error, which is 1.93. Now this is just the denominator. Demonator? I hate spelling. Here's what we're gonna do. Denominator of t-stat. Okay, easy peasy, right? So if you already calculated your t-statistic, which you did, notice that it's the same thing. 15.2 divided by the square root of 62. 15.2 divided by the square root of 62. Easy peasy, right? That turns out to be 1.93. And then you just got to do a little bit of arithmetic there, and then you get a range. Turns out that range is 30.9 to 40.1, okay? Okay, so we can say that we are 95% confident that the true population mean for the garbage discarded by college student households is between 30.9 pounds and 40.1 pounds. That's crazy. Well, one, that's like a lot of garbage, but also we are able to figure out the population range. What somewhere in here is the actual population. It's the actual population value, right? In this case, the mean garbage thrown away, right? The number of pounds, at least, right? Which is pretty wild. And that's the general process. Now, you're probably wondering, Carson, can you please show me some more? Oh, hell yeah. Of course I will. So I've got another example. It'll take a little bit longer, but I highly recommend that you watch it so you can get it for the test, because you might see something, wink, wink, hint, hint, very similar. So I will see you there in just a second.